So, usually when we talk about a medical diagnosis, right, there's this expectation of like a physical reality. You break a bone, you get an X-ray.
Right, yeah.
The image goes up on the light board, and the doctor points to this jagged white line on your radius
Yeah.
and just tells you, it's fractured.
Yeah.
It's a completely undeniable, visible fact. Broken or not broken.
Yeah, it's a very comforting binary, I think. I mean, we really prefer systems where the mechanics are just visible and the categorization is absolute.
Exactly. But when you step into the realm of macroeconomic theory, and specifically, the architecture of national economies, that X-ray machine just completely shatters.
Oh, totally.
Because the bones of an economy, like how capital actually flows, how labor is compensated, or how constraints force optimization, they're completely invisible.
They are, but they are governed by mathematical laws that are just as rigid as human anatomy, which is fascinating.
It is. And welcome to the deep dive. We are speaking directly to you, the dedicated learner, gearing up for the Indian Economic Service, the IES, General Economics GE-01 Paper 2 exam.
And we're tackling this at the DSE or JNU Masters level, right? So we are absolutely not just skimming the textbook today.
No, definitely not. We are taking the engine completely apart, which is honestly the only way to truly master this material.
Yeah, because, this exam is not just some academic hurdle. It's literally the crucible for the people who will eventually dictate the monetary and structural policies of, one of the largest economies on Earth.
Exactly. You cannot just rely on memorization here. You have to internalize the structural logic of it all.
Right. Which brings us to the mission for this deep dive. We are doing an intensive, fully integrated theoretical revision of 3 massive interconnected pillars.
The theory of production, the theory of distribution, and the mathematical methods that basically act as the mortar between them.
Yeah, we are strictly focusing on the mechanics of how an economy actually makes things, which is production, right? And then how it rewards the inputs that made those things, which is distribution.
And of course, the calculus and linear algebra that prove these theories actually work in the real world.
Because you really can't properly understand distribution without the production side. Like why a software engineer earns what they earn, or why a factory owner claims a specific profit margin. You need to understand the mathematical constraints of production first.
Right, they are completely symbiotic. You have to build the theoretical factory first, like establish the production function, before you have any logical basis to figure out the compensation for the workers and the machines.
Exactly.
So to ground this right away in the reality of the IES exam for you, I want to pull 2 specific, pretty formidable questions from recent papers.
Oh, good idea. Let's hear them.
Okay, so first, the 2025 question that requires you to specify the Cobb-Douglas production function, interpret its parameters, and derive its properties.
Okay, class.
Yeah, and second, the 2024 question demanding a strict mathematical proof of Euler's theorem and how it resolves the product exhaustion problem.
Now, on a quick read, those might seem completely unrelated, right? One question looks like it belongs, on a factory floor, and the other belongs in a highly theoretical debate about income inequality.
Right, exactly. But mathematically, they're the exact same conversation.
They really are. The production function basically dictates the physical boundaries, and then Euler's theorem comes in and proves how the revenue generated within those boundaries is distributed without a single cent left unaccounted for.
It's amazing when it clicks together like that. So let's start with that foundation. Section 1, the theory of production.
Right into it.
At its core, we are talking about a mathematical relationship that maps inputs to outputs. And, I really want to move past those introductory recipe analogies. Like, baking cakes just doesn't capture the dynamism of an actual macroeconomic sector.
No, it doesn't. It's too simplistic for this level.
Right, so let's think about a national energy grid. Transitioning from fossil fuels to renewables. We need to actually model that output.
That's a much better framework.
So going back to that 2025 IES question, asking for the Cobb-Douglas production function, let's translate that mathematical notation into spoken English for you.
Go for it.
The Cobb-Douglas function basically states that total output, Q, equals a constant parameter A, multiplied by labor raised to the power of alpha, multiplied by capital raised to the power of beta.
Yes. And I mean, it is the foundational equation of neoclassical production theory, right? It was initially tested by Charles Cobb and Paul Douglas back in the 1920s using real empirical data from American manufacturing.
Which is wild that it holds up so well. But every single variable in that equation carries just immense theoretical weight for the exam. Let's break them down. The parameter A.
Right. A represents total factor productivity. Or in the economic literature, you'll often see it termed the Solow residual or just the state of technology.
So A is basically the multiplier that exists completely independently of how many workers or machines you actually have on the floor.
Exactly. If A increases, it just means society has, figured out a fundamentally better way to organize itself.
Like the invention of the internet or the adoption of double-entry bookkeeping centuries ago, or even just a revolution in supply chain logistics. All of that increases A.
Right. And it mathematically shifts the entire production frontier outward. You get a higher volume of output while holding the physical inputs, the labor and capital, perfectly constant.
Wow. Okay. That brings us to the exponents, alpha and beta. And in the context of the exam, you cannot just call them powers, right?
Oh, absolutely not. If you just call them powers, the examiner knows you don't really grasp the economics. They have a very specific geometric and economic meaning. They are the output elasticities of labor and capital, respectively.
Okay, let's unpack elasticity in this specific context.
Sure. Elasticity here measures the percentage responsiveness of total output to a strictly 1% change in a specific input.
So if your empirical data shows that, say, alpha is 0.6,
then it dictates that a 10% increase in the labor force, assuming you hold the capital stock strictly constant, will result in exactly a 6% increase in total output.
got it. And the relationship between alpha and beta, like how they interact, that determines the returns to scale.
Yeah, that is crucial. If we sum alpha and beta together and the result is exactly 1, we have constant returns to scale.
Or CRS.
Meaning if a semiconductor manufacturer perfectly doubles its workforce and perfectly doubles its lithography machines, the actual output of microchips will exactly double.
Precisely. And in mathematical terms, which you must use on the exam, we say the function is homogeneous of degree 1.
I want to pause on that exact term, homogeneous of degree 1, because it is heavily, heavily tested.
It is the bedrock. Let's define it. A function is homogeneous of degree k if, when you multiply all of your inputs by some positive scalar t, the output increases by t raised to the power of k. So if k is 1, t to the power of 1 is just t. So doubling inputs, which is a t of 2, doubles the output.
Yep.
Constant returns.
Exactly. Now, if alpha plus beta is greater than 1, your k is greater than 1, and you have increasing returns to scale, IRS.
Which is highly relevant in the modern economy, right? I mean, software companies experience massive increasing returns. You double the servers and the engineering team, and your user capacity might quadruple, basically because the marginal cost of distributing code approaches 0.
That is a perfect modern application. But conversely, if alpha plus beta is less than 1, you encounter decreasing returns to scale, DRS.
And that's usually an organizational failure, right?
Yeah, almost always. You double the size of a massive bureaucracy, but the actual output only grows by maybe 50%. Coordination breaks down, communication lines sever, and management just becomes bloated.
But, I want to push back on the Cobb-Douglas model itself for a second.
Yeah.
The math implies this perfectly smooth curve. It implies that a firm can easily, smoothly trade off capital for labor at any point.
Yes, it does.
But in physical reality, substitution is almost never smooth. Like, if I am running a logistics company and fuel prices absolutely skyrocket, I can't simply swap out my delivery trucks for a larger fleet of human drivers who don't have vehicles.
Right.
A human running on foot just cannot meaningfully substitute for a combustion engine in that specific production process. The math feels too perfectly pliable.
And your critique hits on the exact reason economists had to develop alternative production functions. Cobb-Douglas mathematically forces the elasticity of substitution to be exactly equal to 1, constantly, everywhere along the curve.
Which is a huge, rigid assumption.
It is. So if we take your logistics example to its absolute extreme, where inputs cannot be substituted at all, we arrive at the fixed coefficient production function.
Right, developed by Leontief. Let's talk about the geometry of the Leontief production function. If Cobb-Douglas gives a smooth, convex isequence, and isequence are just curves showing combinations of inputs that yield the same exact output, Leontief basically shatters those smooth curves.
Completely shatters them. In the Leontief model, the elasticity of substitution is exactly 0. Inputs must be used in rigid, mathematically locked proportions. Graphically, the isoquants are L-shaped right angles.
L-shaped. So if your production process requires exactly one driver and exactly one delivery truck to complete a route, acquiring a second driver without buying a second truck yields absolutely 0 additional deliveries.
Exactly 0. The marginal product of that second driver is mathematically 0. You are just stuck at the vertex of that L-shaped curve.
Wow, okay, so Cobb-Douglas assumes an elasticity of substitution of exactly 1. Leontief assumes exactly 0. But in the 1960s, economists realized they needed a model that could capture the vast, messy reality existing between 0 and 1, all right?
Right, and that led Arrow, Chenery, Minhas, and Solow to introduce the constant elasticity of substitution function, the CES function, in 1961. And honestly, this is the heavyweight champion of production models because it acts as a generalized parent function.
Okay, let's translate the CES formula for the listener because it is notoriously dense on the page.
It really is.
The CES function states that output Q equals an efficiency parameter A multiplied by a bracketed term. And inside that bracket, we have a distribution parameter delta multiplied by capital raised to the power of negative rho plus 1 minus delta multiplied by labor raised to the power of negative rho.
Right.
And then that entire bracketed term is raised to the power of negative 1 divided by rho.
I know it sounds like a formidable equation, but the key to unlocking it for the IES exam is really focusing entirely on one parameter, the parameter rho.
Rho. Okay, what does it do?
Rho is the substitution parameter.
Rho.
It defines the elasticity of substitution, which economists usually denote with the Greek letter sigma. And the mathematical relationship between them is that sigma equals 1 divided by the sum of 1 plus rho.
Okay, so sigma, the elasticity of substitution, basically measures the physical friction of swapping capital for labor when the relative prices of those inputs change on the open market.
Exactly. And because CES is a parent function, we can use limits to mathematically prove how other functions just collapse right out of it.
Oh, I love this part. Walk us through it.
Okay, if rho approaches infinity, look at the fraction. The denominator of our elasticity, fraction 1 plus infinity, becomes infinite, which means the elasticity of substitution, sigma, approaches 0.
Because 1 divided by infinity is 0.
Right. So the math perfectly collapses into the L-shaped Leontief function we just talked about.
That is so elegant.
But if rho approaches negative 1, the denominator of the fraction becomes 1 plus negative 1, which approaches 0. So 1 divided by 0 means sigma approaches infinity. Capital and labor become perfect substitutes, and the isoquants literally become straight downward sloping lines.
But the most famous mathematical proof required for this exam is showing how the CES function collapses into the Cobb-Douglas function, right?
Yes, that is a classic question.
We established earlier that Cobb-Douglas has an elasticity of exactly 1. So looking at the formula sigma equals 1 over 1 plus rho, for sigma to equal 1, rho has to equal exactly 0.
Right.
But if we just plug 0 into that dense CES equation we read out earlier, the whole thing breaks.
It shatters completely. Let me explain why. If rho is 0, the exponent on the very outside of the bracket is negative 1 divided by 0, which is mathematically undefined. It approaches infinity.
Right.
Simultaneously, the terms inside the bracket become capital to the 0 power plus labor to the 0 power. Anything to the 0 power is 1, so the inside resolves to 1.
So you end up with 1 raised to the power of infinity,
Yes.
which is an indeterminate form. You just cannot evaluate it algebraically.
Well, you can't.
So how do we actually prove the relationship for the examiner?
You have to use calculus, specifically L'Hopital's rule. You start by taking the natural logarithm of both sides of the CES function.
Okay, why does that help?
Because taking the log brings that problematic negative 1 over rho exponent down in front as a multiplier. Then you rearrange the equation into a fraction where both the numerator and the denominator approach 0 as rho approaches 0.
And that 0 over 0 state is the exact trigger condition for L'Hopital's rule.
Exactly. And L'Hopital's rule states that the limit of that specific fraction is strictly equal to the limit of the derivative of the numerator divided by the derivative of the denominator.
So you have to differentiate both the top and the bottom with respect to rho.
Yes. You differentiate the numerator with respect to rho, which requires really careful application of the chain rule, since rho is sitting up in the exponent of the capital and labor variables.
Right.
Then you differentiate the denominator, but the denominator is just rho, so its derivative with respect to rho is simply 1.
Oh, wow. So once you perform that differentiation and then evaluate that new cleaned up expression at rho equals 0, the indeterminate friction just vanishes.
It completely vanishes, and the equation elegantly resolves into the exact log linear form of the Cobb-Douglas function.
Which is the natural log of Q equals the natural log of A plus delta times the natural log of capital plus 1 minus delta times the natural log of labor.
You got it. It is just a stunning mathematical resolution.
It really is. It proves that Cobb-Douglas is just this highly constrained, specific subset of a much broader physical reality. But, what if the physical reality isn't constant at all?
What do you mean?
Well, what if, in a highly complex modern factory, swapping robotic arms for human workers is super easy at low levels of output, but becomes exponentially more difficult as the factory scales up to massive volumes?
Yes. In that case, you must discard the assumption of constant elasticity entirely. You have to graduate to the translog production function.
Translog, which stands for transcendental logarithmic. I know this one is a highly flexible second-order Taylor series approximation.
Yes, meaning it actually includes squared terms and interaction terms between capital and labor.
So it's mathematically modeling how the inputs interact with each other as the scale changes.
Exactly. In a translog function, the elasticity of substitution is not a fixed parameter like rho. It actively changes based on the specific ratios of the inputs you are currently utilizing at that exact moment.
That sounds like it captures a much messier, more realistic world.
It does, though to be fair, it requires incredibly robust econometric data to estimate its numerous parameters, which is exactly why it's usually reserved for advanced empirical research rather than, simple theoretical classroom modeling.
Makes sense. Okay, so we have established the physical shape of the factory. We understand how inputs transform into outputs through these homogeneous and non-homogeneous functions.
Right.
But a rational firm doesn't merely want to produce stuff. It is compelled by the market to produce efficiently, which requires us to shift our analytical lens from just production to optimization. Let's introduce the marginal rates of technical substitution, the MRTS.
Good pivot. The MRTS is the rate at which a firm can theoretically swap capital for labor while holding total output perfectly constant.
So if you give up 2 machines, how many actual workers do you have to hire to keep the assembly line moving at the exact same speed?
That's it. And geometrically for the exam, the MRTS is the absolute value of the slope of the isoquant curve at any specific infinitely small point.
And because of the law of diminishing marginal returns to a factor, that slope is constantly changing.
Always changing.
If I have a factory with 100 machines and only one single worker, adding a second worker will yield a massive surge in productivity. I could probably give up 20 machines and still maintain my output. So the MRTS is very high. The curve is extremely steep.
Right.
But if I have 100 workers and only one machine, adding a 101st worker does almost nothing. They literally have no equipment to use. So I might only be willing to give up a tiny, tiny fraction of machine time to maintain output. The curve goes flat.
That dynamic is exactly why standard isoquants are strictly convex to the origin. They bow inward. As you move down the curve, continuously substituting labor for capital, the MRTS continually declines.
But the physical ability to substitute inside the factory is really only half the problem, isn't it? The firm is bound by a harsh financial reality outside the factory, the budget constraint.
Yes, which introduces the isocost line. The isocost line represents all the possible combinations of capital and labor that a firm can purchase for a strictly defined total cost.
And the slope of this line has nothing to do with engineering. It is determined entirely by the exogenous market prices of the inputs.
Exactly. Specifically, it is the ratio of the wage rate of labor, W, divided by the rental rate of capital, R. So W over R.
And here we reach the absolute core principle of cost minimization. To produce a specific target level of output at the absolute lowest cost, the firm must find the specific point on the graph where its isocost line is perfectly tangent to the required isoquant. Tangency.
Yes, tangency is the holy grail. At that specific point of tangency, the slopes are equal. The marginal rate of technical substitution perfectly equals the ratio of the factor prices, W over R.
Let's translate that math into pure economic intuition. Why is tangency the only rational choice for a business owner?
Because if the slopes are not equal, the firm is bleeding money. It means the physical trade-off rate inside the factory does not match the financial trade-off rate in the open market.
So the firm could lower its total cost by firing a worker and renting a machine, or vice versa, without losing a single unit of total output.
Exactly. Only at tangency is the firm extracting the exact same marginal physical product per dollar spent on the last worker as it is per dollar spent on the last machine.
Okay, that makes perfect sense. Now, let's inject a dynamic element into this, because a firm doesn't stay static forever. It grows.
Hopefully, yes.
Right. So if we solve this cost minimization problem for a small output target, we get a tangency point. If we solve it again for a medium output target, we get another tangency point further out.
Yep.
And if we map out every single one of those optimal tangency points across all possible levels of production, assuming, input prices never change, we trace out a trajectory.
And that trajectory is called the expansion path. It dictates exactly how the firm should mathematically scale its operations from a tiny garage startup to a massive multinational corporation.
And this connects beautifully back to our earlier discussion of homogeneity. If the production function is homogeneous of any degree, or even just homothetic, what does that expansion path look like on the graph?
Well, a homothetic production function implies that the marginal rate of technical substitution depends entirely on the ratio of inputs, not the absolute scale of production.
Okay.
Therefore, if input prices are constant, the expansion path is a perfectly straight ray shooting directly out from the origin.
Meaning the optimal capital to labor ratio is locked in. The firm just scales its machines and its workforce in exact, unvarying proportion forever.
Correct. But if the function is non-homothetic, the expansion path will curve. The firm might become increasingly capital intensive as it scales up.
Which makes sense in reality. Perhaps because large-scale production suddenly unlocks automated technologies that simply don't exist at the artisanal scale. You can't buy half an industrial robot.
Exactly.
Let's use that expansion path to transition smoothly into cost theory. Because in the IES syllabus, there's an explicit, heavily tested duality between production functions and cost curves.
There is. There are two sides of the same coin. The production function dictates the physical reality. The cost function is its exact financial mirror image.
Let's look at the shape of those cost curves, specifically the short-run average cost curve, the SRAC. Why is it universally depicted as U-shaped?
The U-shape is basically the result of a vicious tug-of-war between two opposing economic forces, both operating under short-run constraints. In the short run, by definition, at least one input is fixed.
Usually we assume capital is fixed, like you have signed a lease on a factory and you cannot instantly build a new wing overnight. That lease is your total fixed cost.
Right. So force number one is the spreading out of that fixed cost. When you produce your very first unit of output, that single unit has to absorb the entire monthly rent of the factory.
Ouch. So the average fixed cost is astronomical.
Exactly. But as you ramp up production to 1,000 units, that exact same rent is spread across 1,000 units. The average fixed cost plummets. This mathematically drags the total average cost curve aggressively downward.
Okay. That explains the downward slope of the U. But why does it eventually hit a bottom and curve back up?
That is force number two. The law of variable proportions, or diminishing marginal returns to the variable factor, which is usually labor. Because your factory size is physically fixed, the only way to increase output is to crowd more and more workers onto the exact same factory floor.
And eventually they just run out of machines to operate. They start getting in each other's way.
Exactly. So the marginal physical product of each new worker eventually begins to decline. But because you're still paying them the exact same market wage, the marginal cost of producing the next unit of output begins to rise.
And eventually, this skyrocketing marginal cost completely overwhelms the beneficial effect of the declining average fixed cost.
Precisely. The total average cost bottoms out and begins to aggressively curve upward, completing the U-shape.
But, that is only the short run. The exam specifically asks candidates about the relationship between short-run and long-run cost curves. In the long run, the lease expires. The firm is completely unconstrained. All inputs, including capital, are fully variable.
Right. In the long run, a firm can essentially choose from an infinite number of short-run plant sizes. Imagine plotting dozens of those U-shaped short-run curves on a single graph, each one representing a progressively larger factory size.
Okay, I'm visualizing it.
The long-run average cost curve, the LAC, is derived as an envelope curve. It swoops down and beautifully cradles all of those short-run curves from below.
It never actually intersects them, right? It is perfectly tangent to each short-run curve at a specific point.
Precisely. It never cuts through them. The LAC traces out the absolute lowest possible unit cost for producing any conceivable volume of output, assuming the firm has the time to perfectly optimize its plant size before beginning production.
That's a brilliant way to picture it. Okay, before we close out the theory of production completely, we have to address the concept of productive efficiency. The syllabus explicitly mentions Farrell's measure of efficiency from his 1957 paper.
Yes, Farrell is critical because prior to Farrell, economists essentially viewed efficiency as a single blunt metric. You were either efficient or you weren't.
Right.
But Farrell realized the potential failure was twofold. He split efficiency into two distinct concepts: technical efficiency and allocative efficiency.
It was a massive conceptual breakthrough. Let's define them rigorously for the listener. Technical efficiency evaluates purely physical reality, right?
Right. It asks, is the firm operating exactly on its isoquant boundary? Is it extracting the absolute maximum physical output from the exact physical inputs it is currently consuming?
So if a semiconductor fabrication plant has the capacity to produce 10,000 wafers a day with its current silicon supply and workforce, but say a flaw in its clean room protocol contaminates a batch and they only output 9,000, they are technically inefficient.
Yes. They are operating inside the production frontier. They are physically wasting resources.
And notice, technical efficiency is completely agnostic to market prices. It doesn't care what the silicon costs.
Exactly. Allocative efficiency, however, is entirely about prices. It assumes the firm is already technically efficient, meaning they are physically on the isoquant, but it asks a financial question.
Which is, given the current exogenous market prices of labor and capital, is the firm operating at the specific point on the isoquant where the isocost line is perfectly tangent?
Right. Have they chosen the correct mix of inputs?
I want to use a really modern example for this. Let's look at server farms processing artificial intelligence models. Let's say a company builds a massive data center in a region where electricity, which is our proxy for capital here, is incredibly expensive. But highly skilled engineering labor is very cheap. The data center is technically flawless, no energy is wasted, it is 100% technically efficient. But they built a highly automated, hyper-capital-intensive facility instead of utilizing more human engineers to optimize the code to run on fewer servers.
Oh, that's a great example. In that scenario, the firm is allocatively inefficient. They are on the isoquant, yes, but they are far away from the cost-minimizing tangency point. They chose the wrong input mix for those specific regional prices.
Exactly. So to achieve absolute economic efficiency in Farrell's framework, a firm must possess both. It must not waste physical inputs, and it must select the correct ratio of inputs based on prevailing market prices.
That distinction is paramount. It elegantly bridges the gap between the physical engineering of production and the financial reality of the market.
And that financial reality is exactly where we are heading next. We have minimized our costs, we have optimized our input ratios, and the factory is running perfectly. But the production function now performs a dual role. We used it to derive cost curves. Now, we must use the exact same mathematical properties to determine how the revenue generated by this output is divided among the inputs. We're transitioning to section 2, the theory of distribution.
And honestly, this is perhaps the most historically contentious area of economic theory. We are seeking to answer the fundamental question: what mathematically determines the wage of the laborer, the rent of the landlord, and the profit of the capitalist?
The neoclassical synthesis provided a unified framework to answer this, which is the marginal productivity theory of factor pricing.
Yes.
To understand marginal productivity, though, we first have to understand the specific nature of demand in factor markets. Like if I walk into a store and buy a smartphone, that is direct demand. I derive utility directly from the phone.
Right.
But the demand for the workers who actually built the phone and the machines that assembled it is fundamentally different. It is a derived demand.
The concept of derived demand dictates that a firm does not hire labor for the intrinsic pleasure of employing people. It demands labor strictly and entirely because consumers demand the final output that the labor can produce.
The demand curve for a factor of production is mathematically derived from the demand curve for the final commodity.
Which leads us to the mathematical rule for hiring. If I am a rational, profit-maximizing firm operating in a perfectly competitive market, how do I decide exactly how many workers to employ?
You utilize marginal analysis. You evaluate the very last worker you intend to hire. You determine their marginal physical product, like how many additional discrete units of output did this specific worker add to the total assembly line.
Okay.
You then multiply that physical quantity by the exogenous market price of the good. This yields the value of marginal product, the VMP.
Right. So if a worker adds, say, 5 smartphones a day to the line, and the phone sells for 1,000 rupees, their value of marginal product is 5,000 rupees.
Correct. The firm will continue to hire additional workers up to the exact point where the market wage rate perfectly equals the value of the marginal product of the last worker hired.
So wage equals VMP.
Yes. If the wage is lower than the VMP, hiring another worker adds more to revenue than it adds to cost, which increases profit. You keep hiring.
And if the wage is higher, the worker costs more than they produce, which actively destroys profit. You stop hiring.
Equilibrium is only achieved at perfect equality. The wage equals the marginal product of labor, and the rental rate equals the marginal product of capital.
Now, this sounds incredibly neat and fair. Everyone is paid exactly the value they contribute to the margin. But this elegant theory triggered an absolute intellectual crisis in the late 19th century.
Yes, it did. And this crisis is the subject of the 2024 IES exam question, Euler's theorem and the product exhaustion problem.
The crisis was known as the adding up problem, or the Clark-Wicksteed problem, named after John Bayes Clark and Philip Wicksteed. The challenge was basically this. If a firm pays every single unit of labor its exact marginal product and pays every single unit of capital its exact marginal product,
Right.
is there any mathematical guarantee that the sum of these factor payments will perfectly equal the total output produced?
It's a terrifying question for a firm when you really think about it. If the payments add up to less than total output, who gets the leftover surplus? Does the capitalist just pocket it?
But worse, if the payments add up to more than total output, the firm mathematically goes bankrupt simply by following the optimal hiring rule.
Wicksteed actually published an essay in 1894 arguing that total product would be perfectly exhausted, but his mathematical proof was totally flawed.
It was. It took a review by A.W. Flux to point out that the solution already existed in the realm of pure mathematics. It was Euler's theorem on homogeneous functions, discovered by Leonhard Euler over a century prior.
Let's walk through this mathematical proof exactly as a candidate would need to write it out on the exam page.
Absolutely. So Euler's theorem states that if a function is continuously differentiable and homogeneous of degree 1, which, as we established earlier, means constant returns to scale, then a specific mathematical identity holds true.
Okay, where does the candidate start?
The candidate must begin by formally defining homogeneity. Write the equation. The function f of variables tk and tl is identically equal to t multiplied by the function f of k and l. Here t is just a positive scalar.
Which simply says that scaling both inputs by t scales the total output by exactly t.
Right. Step 2 is the calculus. We must differentiate both sides of this equation strictly with respect to t.
Okay.
On the left side, you must apply the multivariate chain rule. You take the partial derivative of the function with respect to capital, and you multiply it by the derivative of tk with respect to t, which is simply k.
Right.
Then you add this to the partial derivative of the function with respect to labor, multiplied by the derivative of tl with respect to t, which is simply l.
Wait, let me clarify that left side for the listener just to be safe. The partial derivative of the production function with respect to labor is, by strict economic definition, the marginal product of labor.
Yes.
And the partial derivative with respect to capital is the marginal product of capital.
Exactly. So the left side cleanly becomes capital multiplied by the marginal product of capital plus labor multiplied by the marginal product of labor.
And what happens to the right side of the equation when we differentiate it with respect to t?
Well, the right side was simply t multiplied by total output q. The derivative of t times q with respect to t is just total output q.
So we arrive at the final identity. To finalize the proof, we evaluate the entire expression at t equals 1.
And the result is absolute mathematical perfection. Capital times the marginal product of capital plus labor times the marginal product of labor equals exactly q.
The product exhaustion problem is definitively resolved. Under the strict mathematical condition of constant returns to scale, if you pay every single factor its exact marginal product, the total output is perfectly, cleanly exhausted.
The wage bill plus the capital rental bill perfectly equals total revenue. There is zero remainder.
The economic implications of that are just staggering. It basically provides the mathematical architecture for the entire neoclassical defense of competitive free markets.
It does. It suggests a world devoid of systemic exploitation. The worker is not robbed of surplus value, and the capitalist does not extract unearned rents. The pie is partitioned perfectly without remainder.
But, and this is a massive but, we must be brutally clear about the constraints of this theorem for the exam. It only holds if the production function is homogeneous of degree 1.
Exactly. If the economy exhibits increasing returns to scale, meaning a homogeneity greater than 1, Euler's theorem mathematically dictates that paying marginal products will result in a sum that is strictly greater than total output.
The math breaks. The firm literally goes bankrupt by following the rule.
Which means marginal productivity cannot possibly be a complete universal theory of distribution. It is highly conditional.
And that limitation is exactly why the IES syllabus demands we study alternative macro distribution theories. The exam frequently asks candidates to contrast the neoclassical marginal productivity approach with classical and post-Keynesian models.
Yes. Let's look at David Ricardo's theory, which is often referred to as the Korn model.
Right. Ricardo's 1815 essay completely ignores marginal calculus. His theory of distribution is rooted in the physical scarcity of land and the differing fertilities of soil. Let's trace his logic.
Okay, an economy starts by farming the most fertile grade A land. But as the population inevitably grows, the society is forced to cultivate less fertile grade B land and eventually terrible grade C land.
And as you move to worse land, the law of diminishing returns asserts itself fiercely. It requires vastly more labor and more capital to produce the exact same bushel of corn on grade C land as it did on grade A.
So the fundamental cost of producing food rises globally across the economy. What does that actually do to distribution?
It creates a massive structural squeeze on the capitalist. According to the classical wage fund theory, workers must be paid a subsistence wage, literally just enough corn to survive and reproduce.
But because food is now much harder to grow, the nominal cost of that subsistence wage skyrockets.
Exactly. The capitalist is forced to pay a higher and higher wage bill just to keep the workers alive, which viciously compresses the capitalist's profit margin.
But someone is making money here. If the price of corn is universally high, the people who own the ultra-fertile grade A land are suddenly extremely wealthy.
They are. The landlords capture the entire surplus as differential rent. Rent arises entirely from the unequal fertility of land.
So in Ricardo's grim, long-run steady state, capitalist profits are mathematically squeezed to absolute zero, workers are perpetually trapped at bare subsistence, and the landlords consume the entirety of the economy's surplus value simply by holding a monopoly on fertile dirt.
It is an incredibly dark, zero-sum view of distribution based purely on physical limits. Now, contrast that deeply with Nicholas Kaldor's macro distribution model from 1956.
Kaldor completely abandons the micro-level marginal product entirely and builds a Keynesian framework.
Kaldor's model relies on a fundamental behavioral assumption. Different socioeconomic classes have fundamentally different marginal propensities to save.
Specifically, he posits that the capitalist class saves a much higher percentage of their profit income than the working class saves from their wage income.
Okay, but how does that behavioral trait actually determine macroeconomic distribution?
Well, Kaldor argues that in a macroeconomy, total investment is an exogenous variable. It is determined by the animal spirits of entrepreneurs. And for the economy to maintain equilibrium at full employment, total savings must exactly equal total investment.
Right, standard Keynesian identity. So if investment suddenly rises, the economy fundamentally needs more savings to finance it. How does the economy generate those extra savings?
Through a massive systemic shift in income distribution, prices rise relative to wages, which forcefully shifts a larger share of national income away from the low-saving workers and into the pockets of the high-saving capitalists.
And as the capitalist share of income expands, total national savings naturally rise until savings perfectly match the new, higher level of investment.
Exactly. In Kaldor's model, the distribution of income isn't about marginal productivity. It is a flexible, dynamic balancing mechanism required to maintain macroeconomic equilibrium.
It is fascinating. Neoclassical marginal productivity focuses on engineering efficiency and micro-level calculus. Ricardo focuses on land scarcity and class conflict. Kaldor focuses on savings rates and macroeconomic stability.
They're looking at the exact same economy through entirely different conceptual lenses. And the IES examiner will absolutely expect you to seamlessly pivot between these lenses, evaluating their underlying assumptions.
It's so true. Okay, we have discussed the physical reality of production and the economic theories of distribution. But throughout this entire conversation, we have been leaning heavily on optimization, minimizing costs, maximizing output, equating margins.
We have.
We need to expose the mathematical engine that actually computes these optimal states. We are moving into section 3, Mathematical methods in economics.
Because we cannot rely on simply drawing tangent lines on a graph, especially for the exam. To solve multivariable economic models, we require calculus. Specifically, the method of Lagrange multipliers, developed by Joseph Lagrange.
It's the absolute bedrock of constrained optimization. Let's break down why we actually need it.
In standard unconstrained calculus, to find the maximum or minimum of a function, you just take the first derivative, set it to 0, and solve. Simple.
But economic reality is never unconstrained.
Oh.
You want to maximize your factory's output, but you are shackled by a strict financial budget. Or you want to minimize your cost, but you are legally bound by a contract to deliver exactly 10,000 units.
You have an objective and you have a barrier. You cannot juggle two separate equations in a standard derivative. The genius of the Lagrangian method is that it elegantly collapses the objective function and the constraint equation into a single, unified mathematical object.
Let's construct the Lagrangian function, usually denoted by the script letter L. The formula is L equals the objective function minus a new variable called lambda multiplied by the constraint equation set exactly equal to 0.
Let's apply that to a firm actively minimizing cost. The objective function is total cost, which is wage times labor plus rental rate times capital.
And the constraint is that the production function must equal the target output Q. So the constraint equation rewritten to equal 0 is Q minus the function f of k and L equals 0.
So the Lagrangian becomes cost minus lambda times that constraint. Once this single equation is built, the calculus takes over. We take the partial derivatives of the Lagrangian with respect to labor, with respect to capital, and with respect to lambda.
And we set all three partial derivatives exactly equal to 0. These are our first-order conditions.
Yes. When you solve that system of three simultaneous equations, the mathematics forcefully drives you to the optimal solution.
The equations automatically verify that the ratio of the marginal products equals the ratio of the factor prices, achieving our MRTS tangency condition mathematically, while the derivative with respect to lambda guarantees that you perfectly hit your production constraint.
It acts as an algorithmic heat-seeking missile, finding the exact optimal point on the curve.
But I really want to drill down into the new variable we introduced, lambda.
Yeah, lambda.
In purely mathematical terms, it's just an artificial multiplier. But what is its actual economic identity? In plain reality, what does lambda represent?
Lambda is arguably the most important single number in the entire optimization problem. It is officially known as the shadow price of the constraint.
Shadow price. It sounds like an illicit market term. Let's ground this. I don't want an abstract definition. Give me a physical high-stakes example where the shadow price actually matters to a policymaker.
Okay, let us step outside the factory. Imagine a national health ministry during a severe pandemic. The objective function is to maximize the number of lives saved.
Okay.
The absolute rigid constraint is the physical infrastructure. The country possesses exactly 5,000 intensive care unit beds.
So they build a complex Lagrangian model integrating infection rates, medical staff, and resources, subject to the strict constraint of 5,000 beds. They run the optimization, and the math spits out an optimal allocation strategy, and it also generates a numerical value for lambda. Let's say lambda equals 3.2.
What does that 3.2 actually mean to the Minister of Health?
Yeah, what does it tell them?
It represents the marginal value of relaxing the constraint by exactly 1 unit. In this scenario, lambda tells the minister that if they can somehow procure just one single additional ICU bed, raising the constraint from 5,000 to 5,001, the optimized system will save exactly 3.2 more lives.
Oh, wow, that is incredibly powerful. Lambda is literally the marginal opportunity cost of the barrier itself.
Precisely. In a standard firm's cost minimization problem, if the constraint is a production quota, lambda is the mathematical equivalent of the firm's long-run marginal cost. It reveals the hidden shadow cost to the objective function of being restricted by the constraint.
But the Lagrangian method strictly requires smooth, continuously differentiable functions. It requires internal tangency. What happens when the economic reality is not a smooth curve, but a rigid boundary?
Right.
Like, what if a factory has exactly 500 hours of machine time available? It cannot physically use 501 hours, but it is perfectly allowed to use only 400 hours if it wants to. The constraint is an inequality. Calculus struggles with rigid boundaries.
Which necessitates the shift from calculus to linear programming. Linear programming models optimize linear objective functions subject to linear inequality constraints.
It defines a feasible region, a multidimensional geometric polygon, and mathematically searches for the optimal solution at the extreme vertices of that polygon.
Yes, and the IES syllabus specifically focuses on a profound mathematical symmetry within linear programming, the concept of duality. Every single optimization problem, which we call the primal problem, casts a mathematical shadow. That shadow is the dual problem.
The symmetry is beautiful. Let's define the primal for context. Imagine a manufacturer attempting to maximize its total physical output. It is constrained by strict inventory limits. It only has 100 tons of steel, 50 megawatt-hours of electricity, and 200 hours of labor sitting in the warehouse.
The firm solves the primal linear program to find the absolute maximum possible volume of output.
Okay, that is maximizing an objective subject to resource constraints. What is the dual problem looking at?
The dual flips the entire architecture upside down. Instead of maximizing output, the dual seeks to minimize cost. It asks the strict accounting question. What is the absolute minimum imputed monetary value we can assign to those specific resources in the warehouse, the steel, electricity, and labor, such that the total valuation of the inventory perfectly equals the value of the final output they can produce?
And the mathematical solution to the dual problem generates specific imputed values for each of those resources.
Yes. And according to the strong duality theorem, if an optimal solution exists for the primal, an optimal solution must exist for the dual, and their final objective values will be identical.
The maximum physical output value is exactly equal to the minimized imputed resource cost.
Furthermore, those imputed resource values calculated by the dual are the shadow prices. They are the exact linear programming equivalents of the Lagrange multipliers we just discussed.
It is an incredible web of mathematical consistency. Whether you use calculus or linear algebra, the shadow price inevitably emerges. Speaking of linear algebra, we have to discuss matrices before we run out of time.
Yes, the final major model we need to cover is the Leontief static input-output model. This model essentially takes the rigid, fixed coefficient production function we discussed way back in Section 1 and scales it up to map an entire national economy.
Because Wassily Leontief realized that viewing an economy as a collection of isolated, independent industries is a fundamental error. An economy is a massive circular web of inter-industry dependencies.
It is. To build automobiles, you require steel. But to forge steel, you require electricity. To generate electricity, you require coal. And to mine and transport coal, you require trucks, which are built by the automobile industry.
It is an infinite loop of intermediate demands. How on earth does a central planner or an economist calculate the total requirement if a shock hits the system? Like if the government decides to build a new national highway system, creating a massive exogenous final demand for concrete, how do we mathematically know if the economy can handle it?
You build a matrix. Leontief assumed constant returns to scale and fixed technical coefficients. He created an input-output matrix, traditionally denoted as matrix A.
Oh.
Every column in matrix A represents an industry. The numbers in that column dictate exactly what fraction of inputs that industry must purchase from every other sector to produce a single unit of its own output.
So it's basically a comprehensive recipe book for the entire economy. But how do we solve the infinite loop?
We use linear algebra, specifically matrix inversion. We start with the identity matrix, IU, which represents total gross output. We subtract the input-output matrix A, which represents the intermediate goods consumed during production.
The result, the matrix I minus A, represents the net output available for final exogenous demand. To find the required gross output, we must invert this matrix.
The famous Leontief inverse. The matrix I minus A inverse.
When you multiply the Leontief inverse matrix by a vector representing the new exogenous final demand, like the new highway system, the linear algebra instantly and simultaneously calculates the required gross output vector for every single sector in the entire economy.
It automatically calculates the direct demand for the concrete, the indirect demand for the limestone to make the concrete, the indirect demand for the electricity to mine the limestone, the coal for the electricity, all the way down the supply chain, converging to a finite, totally exhaustive requirement.
It is the ultimate macroeconomic planning tool.
It is. But it only yields valid results if the Hawkins-Simon conditions hold true. The principal minors of the I minus A matrix must be positive.
Economically, what does that ensure?
It ensures that an industry does not consume more than 1 unit of its own output to produce 1 unit of its own output. If that condition fails, the economy is physically unviable. It consumes more than it creates. It's a black hole.
Wow. This has been an incredibly deep and intense synthesis of the material. Let us briefly recap the architecture we built today.
Good idea.
We started on the factory floor, defining the physical parameters of production using Cobb-Douglas and CES functions. exploring how L'Hopital's rule binds them together. We optimize the factory using the Lagrangian method, finding the tangency between the MRTS and factor prices, and generating the shadow prices of our constraints. We then examine how the revenue is distributed, using Euler's theorem to prove that under constant returns, paying marginal products perfectly exhausts the product, while contrasting that with Ricardo's and Kaldor's macro distribution frameworks. Finally, we scaled it all up using Leontief's matrix algebra to model the entire national web.
It is a cohesive, logically watertight system of thought. But the ultimate test is applying this framework under the strict time constraints of the IES exam.
Exactly.
Based on the structural trends of the GE-01 Paper 2 exams over the last decade, I have formulated 3 highly anticipated mathematical patterns that candidates must be prepared to execute flawlessly in 2026.
Okay, let's outline the battle plan. What is prediction 1?
Prediction 1, the calculus derivation of a cost function from a given production function. You will almost certainly be handed a specific Cobb-Douglas production function and asked to mathematically derive the long-run total cost function.
What is the exact sequence of steps a candidate must show to secure full marks?
You must formally establish the Lagrangian function, minimize total costs subject to the production target Q. You take the first-order partial derivatives with respect to k, L, and lambda and set them to 0. Crucially, you must divide the first 2 conditions by each other. This eliminates lambda and mathematically proves the tangency condition. MRTS equals W over R.
Wait, let me interrupt there. Once they establish that tangency condition, why is the next step to isolate one of the physical variables, like capital? What does that isolated equation actually represent?
Excellent question. When you isolate K strictly in terms of L, W, and R, you have mathematically defined the expansion path. You have derived the specific trajectory of optimal input ratios.
I see.
The final step is to substitute this expansion path equation back into the original production constraint. You solve for labor strictly as a function of output Q and prices W and R. You do the same for capital. Finally, you plug those optimal input demand functions into the total cost equation. The resulting formula is your long-run total cost, expressed entirely independently of physical inputs.
Understood. That is a rigorous process. What is prediction 2?
Prediction 2. The formal proof of Euler's theorem and the resolution of the product exhaustion problem. We walked through the chain rule differentiation earlier. The examiner will be looking for the explicit definition of homogeneity, the correct application of the multivariate chain rule, and a concluding sentence explicitly stating that the identity resolves the Clark-Wicksteed adding up problem by proving 0 surplus under constant returns.
And the final prediction?
Prediction 3 moves away from pure calculus and into comparative macroeconomic theory. Expect an essay question requiring you to critically contrast Ricardo's classical distribution theory with Kaldor's post-Keynesian distribution model.
With the key differentiator being their fundamental drivers.
Precisely. You must articulate that Ricardo's model is driven by physical constraints, the inelastic supply of land, and the law of diminishing returns driving subsistence wages and squeezing profit. Conversely, you must articulate that Kaldor's model is driven by behavioral macroeconomics, specifically, the differing marginal propensities to save between capitalists and workers, which forces income distribution to shift dynamically to maintain equilibrium with exogenous investment.
That is a formidable analytical toolkit. You have the mechanics, the proofs, and the historical context.
Yeah.
But before we sign off, I want to leave you, the listener, with a final provocative thought to mull over as you return to your notes.
Let's hear it.
We spend a significant amount of time discussing Euler's theorem, which proves that total output is perfectly exhausted if, and only if, the economy operates under constant returns to scale. The math is elegant and clean.
But it is highly conditional.
Exactly. Look at the reality of the global economy today. We are dominated by digital platforms, artificial intelligence, and network effects. These are industries defined by massive, overwhelming, increasing returns to scale.
They absolutely are.
The initial fixed cost to develop a foundation AI model is billions of dollars. But the marginal cost to copy it and deploy it to a new user is practically 0.
Which violently breaks the assumption of homogeneity of degree 1.
It shatters it. If you attempt to apply the neoclassical rule in a digital monopoly like paying every engineer and server their exact marginal product in a system with increasing returns, the calculus mathematically dictates that the sum of the payments will exceed the total output.
The firm would instantly bankrupt itself.
The elegant neoclassical math breaks down entirely in the digital age. So, if the marginal productivity theory cannot explain the modern tech economy, I leave you with this question. Who is actually capturing the massive surplus being generated? And what new mathematical model will we need to build to explain it?
That is the absolute frontier of economic theory. It is exactly the kind of critical extrapolation a future economic advisor must be capable of.
Think deeply about the limits of the models you are memorizing. Keep pushing the boundaries of the theoretical architecture. Good luck with your revision.